So this video discusses the maximum power transfer theorem. So if we look here, we see this is like a power supply like we use in lab. And this power supply is got obviously quite a bit of electronics and stuff in it, but it's going to output current to some sort of load, and of course that current is going to return back in there. Now so this load resistor could be, theoretically any kind of load. So let's just kind of think about a radio. So like here's a picture of a CB, Citizens Band radio, and so obviously it has a lot of electronics in there. It's got to amplify the signal and put it onto the transmitting frequency, and then we want that to be passed out to the antenna so that we can transmit with as strong a signal as possible. So we want to have the maximum amount of power possible getting here to the load. So like in this case, I just have like a generic resistor as a load, but in this case the antenna is the load. So the antenna just kind of acts essentially like any resistor would, but it's actually going to be outputting radio waves, and so we want to be able to transmit as much power. We want as much power as possible to get to the antenna so that we can transmit that signal as clearly and as far as possible. So that's kind of the idea of the maximum power transfer. So if we consider one of these big fancy electronic boxes here, whether it's the power is just a general power supply or whether it's something more complicated like a radio, we have all these electronics are in here. So this blue box down here just kind of represents some particular circuit that could possibly be inside of one of these two boxes. And so Thevenin, we've already discussed Thevenin. Thevenin says that we can take everything inside of this blue rectangle here, all this complex stuff going on, and we can simplify it down to a DC voltage supply, or if you're doing AC, it could be an AC voltage source. Okay, Thevenin works for either one, and Thevenin says that we can simplify it down to just a voltage source, whether it's AC or DC voltage source, and a impedance. Okay, so in DC we just all our impedances are resistances, but if you're doing AC, this could actually have some inductors and capacitors in here, so it would be a full impedance. But for both AC or DC, if all you have is resistors, then you would just have a resistor component, which we would call R Thevenin. So we have this voltage supply which has a value, and that value is called E Thevenin, and a impedance or a resistance. If all you have are resistors inside of here, it would just be a resistance, again whether it's AC or DC, and so we would have this resistance R Thevenin. Okay, and so that's the idea of Thevenin. Says that we can take all this big complex fancy stuff and simplify it down into just a voltage supply in series with a Thevenin resistance. And then at points A and B here, points A and B, we're going to connect to our load. Okay, so if we're thinking about this antenna example over here, right, here's my nodes A and B for the antenna. And so the idea here is that we want to get the maximum amount of power as possible to the load. So the question becomes, what value of load resistance is going to give me the maximum power. So now keep in mind here that this Thevenin resistance or impedance is kind of dictated by the needs. So if it's actually going to be some kind of radio, you know, we've got to be able to select the frequencies, and we've got amplifiers in here to amplify the signal and all this. And so the electronics in here we really can't do anything about, because if we do, then we may not be able to actually get the signal formatted the way that we need it so that we can transmit it. So we're kind of limited here. So what we want to do is basically do what's sometimes referred to as an impedance match. And so we want to match this load to the Thevenin equivalent. And the maximum power theorem is pretty straightforward. It says to get the maximum amount of power to the load, you simply have to make sure that the load resistance is equal to the Thevenin resistance. Okay, it's that easy. So in the same thing, even if you're talking about AC circuits, if all you have is resistors, you have a load resistance and you have a Thevenin resistance, and so you just need to make sure that those resistances are equal. Now for AC, if you are doing AC, you may also have some capacitors and inductors in there, so you have a full impedance with the reactance. So you might have some capacitive reactance and you might have some inductive reactance. And so the maximum power theorem basically says that you want to, if you have in your Thevenin, if you have a lot of capacitance, then what you need to do for your load is you need to put a lot of inductance in your load so that the inductive reactance and the capacitive reactance cancel out, and you're left only with resistance anyhow. Okay? So, you know, so it really kind of comes down to the resistance. Now, I will do an example here in a second video looking at AC specifically and looking at the reactances. But in this video here, I'm going to be looking at whether it's AC or DC voltage. Does not matter, because all we're doing is resistances. So we're ignoring, we're saying there's no reactances in the circuit anywhere. So we just have an E Thevenin with an R Thevenin resistance, and then we're going to add in a load resistance. And again, what we want to do, right, is we need to match these. So it's whatever our Thevenin resistance is, we just want that to equal, we want our load resistance to equal that. So that's, like I say, sometimes it's referred to as impedance matching or load matching. And again, you know, we can't really do much about the electronics in this radio, because if we start messing with that, then we can't actually transmit the signal the way we want to. So the impedance in here is kind of dictated by what we need to do to actually generate a radio signal that we can actually send out to the antenna. So we need to therefore match the antenna to our radio device. And so one thing I want to point out here, right, maximum power transfer says it means we're going to get the maximum power to our output device. So we're going to get our maximum power to the antenna, or to whatever our load might be. And so we there are cases, as we'll see here when I do this example, there's cases where you're using lots and lots of power, but it's not getting to your antenna. It's being used up inside of your electronics or whatever inside of your device, whether it's a power supply or radio or TV or whatever that device may be. Okay, so maximum power transfer means the maximum power to the load, not the maximum power that your voltage source is outputting. Okay, so let's just take a look here. We have our Thevenin circuit here. I guess I'll redraw it down here so we can see this. And what we're going to do is do this table here. So we have a voltage source, and I'm just going to try to draw it more as a generic voltage source, because again, this could be an AC or a DC voltage source. Okay, so this is going to be E Thevenin, and just for this example, I'm going to say that this is actually going to be 20 volts. So we have E Thevenin, which is going to be 20 volts, and I'm saying that I have an R Thevenin, which is 10 ohms. And so the question then becomes, what resistance for my load resistance should I choose to get maximum power to the load? Okay, so I'm trying to get maximum power to the load. All right, so now again, I can't do anything with E Thevenin and R Thevenin because those have already been dictated because of my device, whether it's a radio or power supply or whatever, and so I can't do anything with that. But what I can do is I can adjust my load or choose a load that I'm going to attach to it to give me maximum power to the load. And so I just want to remind you, right, this is a series circuit. We have R Thevenin plus R load. So the total resistance, R total, is simply the sum of R Thevenin plus R load. Okay, and so R total here, so if you look, I'm going to just do some examples here. So R Thevenin is fixed. It's going to be 10 ohms. R load, I'm going to vary it. I'm going to use 5 different values here just so that we can see the maximum power is going to occur as they stated before. Maximum power is going to occur here where R Thevenin and R load are equal. Okay? So, right, that's what maximum power theorem tells us. But what I'm going to do is just look at these different values. So I'm going to look at 2 different values above and 2 different values below the maximum value to see. So anyhow, so we have our total here, and we know then from Ohm's law that the total current, I total, okay, so I total is equal to E Thevenin divided by R total. Okay, so that's going to be my total current. It's a series circuit, so it's the same current everywhere. And so, so this is going to be in amps. And all right, so it's E Thevenin divided by R total. And so that gives me the if we calculate that for these various resistances, okay, so the first case, our total resistance is 110 ohms. And so if we calculate that, then we're going to get a total of about 182 milliamps, right, or 0.182 amperes. All right. In the next case, our load is twice, right? In this case, the first case, right, our load was 100 times the size. The resistance was 100 times, or excuse me, it was 10 times the resistance of our Thevenin. Okay, so our total was 110. So now in this next case, our resistance is 20 ohms, so our total resistance is going to be 30 ohms. And so if we calculate our current, then our current is basically going to be, right, 20 divided by 30. Okay, so the current would be 20 divided by 30, or 2/3, which means it's going to be 0.667 amperes. All right, so in the next case, right, we have, again, E Thevenin is 20, and this is the one that they're telling us that should be the maximum power. All right, but I just want to verify that. So this one should be the maximum power here. And so for maximum power, or what they're telling us or predicting to us that's going to be maximum power, I have R Thevenin is equal to R load, which gives me a total of 20 ohms. And I've got E Thevenin is 20 volts, right? So 20 divided by 20 is simply equal to 1. So this is going to give me 1 ampere. All right? So I have 1 ampere at this maximum power level, or what they predicted or told us at least that is maximum power. All right, so in the next case, let's say that our load is half of R Thevenin. Okay, so our load is 5 ohms. Okay, so our load is 5 ohms. And so if we were to calculate that, right, our total would be 15 amperes. So we would have 20 volts divided by 15 amperes, right, which gives us, divided by 5, that gives us 4/3, or 1.33 amperes. And in the last case, our load is 1/10 of R Thevenin, or 1 ohm. And so my total resistance is 11 ohms. So I got 20 divided by 11 ohms. And so 20 divided by 11 ohms is going to give me 1.82 amperes. All right. And so one thing here, again, I want to point out to you, my current, all right, the current is going up. So as the resistance of the load is going down, the magnitude of the total current is going up. So I actually have more current. I have more current over here . So I have more current in these last two cases than I did for what they told me was going to be maximum power. All right, so let's look at total power. Okay, so total power, all right, we know from DC class, right, that power in DC is simply equal to the voltage times the current. However, if we use Ohm's law, right, we can get that the voltage is equal to I times R, and so therefore we can say that power is equal to I squared R. All right, and this is for DC. And for AC, we haven't maybe discussed that too much yet, but for AC, power is actually, remember that voltage and current have phase shifts in AC, so we have to worry about the phase shift. So power is equal to the voltage times the current, the magnitude of these, times the cosine of the angle between the two. However, inside of a resistor, the voltage and the current are exactly in phase. And so the angle between the two is 0, and the cosine of 0 is simply 1. All right, and so inside of a resistor, power is still I squared R. It doesn't matter whether it's AC voltage or DC voltage, right? The power inside of a resistor is and always will be I squared R. Okay, one more time. Power inside of a resistor is I squared R. So if we have total power, okay, whether it's AC or DC, if I know the magnitude of the current, I don't have to worry about the phase angle, even in an AC, because it's simply I squared the magnitude of the current, I squared times the resistance. So if I'm looking for total resistance or total power by the supply, okay, so this is the total power that this voltage source has to dish out. Okay, so total power is equal to I squared times R. And so if we look here, then we take I, square that, and multiply it times the total resistance, I squared times R total for total power. And so in this first case here, my total power is going to be 3.64 watts. Okay, so this is going to be 3.64 watts. Okay, and the next case, right, we're going to take I squared times the 30 ohms. Okay, so this 0.667, it's actually 0.6666666 amperes. Square that, multiply it times 30, and that's going to give me 13 watts. Okay, so 13.3 watts, right? So the power is going up, right? And our current is going up. We're squaring the current, so we kind of expect that. Okay, so if we look at what they're telling us maximum power is here, we're going to take 1 amp squared times 20 ohms, and so that of course is going to be 20 watts. Okay, now remember, this is the power supplied here. This is the power that the voltage source is supplying, but it's not what's getting to the load. This is just total power being used. Okay, so if we go to the next one, we're going to have 1.333333 squared times 15 ohms, and that's actually going to give us 26.7 watts, right? So again, our current has gone up, 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 up. Current is increasing, and therefore our total power that is being fed out from the voltage supply is increasing. So if we do the last case, the total is 11 ohms. Okay, so 11 ohms times 1.82 squared, and that's going to give us 36.4 watts. Okay, so it's hopefully, it's very obvious. Okay, this is the max power supplied. Okay, so this is the maximum power that the voltage source has to dish out. Okay, so when our current is at the highest, that means that our voltage source has got to be dishing out a lot of power. Okay, but that's not maximum power transferred. Okay, so let's look here now at our load. And again, our I squared R so I squared times R gives us power, but in this case we're looking at just the power at the load. Okay, just the power at the load, so our load. So we're going to take and look at the first example here. The load is really big. It's 100 ohms, right? The load over here is 100 ohms. So, but our current is actually really small, right? It's actually a fraction of an amp here. And so when we square this, when you square 0.182, right, anytime you square a fractional number, it actually gets smaller. And so 0.182 times squared times 100 ohms, because we're only looking at the load resistor, means that 3.3 watts, okay, so 3.31 watts are getting to the load. Okay, so 3.31 watts are getting to the load, which means that we're losing about 0.33 watts here, right? So there's 0.33 watts being used up inside of our electronics of the radio or the power supply. Now, if we look at the next case, right, we're going to take 0.66 squared times the 20 ohms. Okay, so 0.667 or 0.66666 squared times 20 ohms, and that gives us a total wattage of 8.89 watts. Okay, so 8.89 watts is making it to the load. Okay, so my power is going up. The power to the load has increased, right, more than doubled. All right, and so I didn't really put a column here for this, but the power used by inside of our Thevenin was about 0.33 here, and then here it's about 5 something, about 5 watts there. And then let's look at the loaded, what they call us max power now. Okay, so max power, we have 1 ampere squared. So we have 1 ampere squared times the 10 ohms of the load resistance, which is simply 10 watts. 10.0 watts if we want 3 significant digits. All right, so let's look at the next case here then. We have 1.33 amperes, but our load is only 5 ohms. Okay, so our load has dropped down to 5 ohms, but our current has increased, so we got 1.33 amps. But when you do this, you're back to about 8.89 watts. Okay, so notice if we look at this, right, our load here was twice the amount of the maximum power value of 10, and we ended up with 8.89 watts. And then here on this example, our load resistor is 1/2 of that. Okay, so the factor of 2, you notice that those two actually match. All right, and then if we do the last example, we had 1.82 amperes, so we had a lot more current flowing through, but we only have 1 ohm at the load, which means we're back to about 3.31 watts. Okay, and so again, this was 1/10. Our load was 1/10 of our Thevenin, and for the first example, R load was 10 times R Thevenin, and so you see those values matching up too there. All right, but you can see that yes, indeed, maximum power is occurring when R Thevenin is equal to R load, or the load resistance is equal to that Thevenin equivalent. Okay, that is when we receive maximum power. All right, so you can see that there. That is the maximum power transferred. Okay, so again, it wasn't actually the maximum amount of power supplied by the voltage source, but it's the maximum amount of power that actually got to our load. So again, if we kind of go up and think about the transmission, if we're trying to transmit out a message out through a radio, then we want the maximum amount of power getting out and being transmitted as possible, so that the message goes as far as possible and is as clear as possible to anyone receiving it. Then we have to we have to balance or match our antenna to match the Thevenin of the radio that we're attaching it to. So we have to balance that. So for maximum power, we want R load equal to the Thevenin resistance. Okay, and again, this is true for AC or DC, and we just want those resistance values to match. Okay. Now for AC, if you do have reactances, then you actually have to get the reactances to cancel out, so that effectively all you have left is the resistance. And so I'll do a separate video on that.